Hi everyone. In the last couple of videos, I have shown how to create simulations of the projectile motion. If you have not seen these videos, please take a look there. They are very interesting. Today, I'm going to show how to create a simulation of a two-dimensional motion that is also very important. This is the circular motion. And before we start, I would like to show you already the simulation resulting from the code piece we are going to learn today. So this is the simulation resulting from the code piece we are learning today. And we see a circular motion where it's shown the velocity vector and acceleration vector. This simulation is interesting to show to the students the fact that the velocity vector is always tangent to the trajectory and that the acceleration vector in this case is always pointing to the center of the trajectory. So if you think creating animations like this should be interesting to your classes, please stay until the end of the video and don't forget clicking the like button, subscribing to the channel and activating the bell. So let's start. So let's start by defining the radius of the motion and the angular velocity. I'm going to insert this comment here because usually the angular velocity is referred to the Greek letter omega, but here I'm going to use W, and the period of the motion is related to the angular velocity via this equation. Let's now define the horizontal component of the position and the vertical component of the position. I would like also to define the velocity components via the derivative of the position components. So we have these, and also the acceleration components via the derivative of the velocity components. There. I would like to make first a static representation. So I'm going to define x max here that's going to be used to determine the axis range. And I'm going to use this command set draw defaults to set the options that are going to be the same for both the static representation and the animation. So the first of them is proportional axis and x range, y range, point type, point size, line width, antics, and head length. Determine the size of the vector heads, and let's set it to this value. There. To generate this static representation, we need to choose a instant. So let's define TP to set this instant, and let's use polar to draw the trajectory. and points to draw the particle position in the instant TP. There. And here we have the static representation. This representation is interesting because if we change the value of TP, then this representation is going to change. For example, if I set TP to 1, then the particle position changes here. If I change TP to, for example, the period divided by 2, then the particle is here. I would like to insert also the velocity vector there. So I'm going to add here color green vector. So this vector is going to start in the position where the particle is, and its components are these. And I'm going to divide this vector by 2 so that it does not appear too long there. So here is the representation of the velocity vector. We can also insert the representation of the acceleration vector. That is also very important in this motion. So I can add this. So I'm going to put this vector there in red. And its components are these. And I'm going to divide it also by 2 so that it does not appear too long there. And again, if I change the value of the TP, then the position and the vectors are going to change currently. Now let's generate the animation. In order to do so, I'm going to define a Tmax. So let's set it initially to the period of the motion and the number of frames. And let's set the file name. And on the terminal, make a list to generate the list of frames and gr2d to draw each frame. And initially in each frame, we'd like to show the particle. So let's insert points and the x component of the position, the y component of the position, and let's tell make list the time interval and the time step, and hope everything's okay. And our animation has been generated. Let's open it. It's here and it looks like this. So we see that we have a circular motion being shown there, but it's interesting to add other things. For example, let's add the velocity vector. So we have the same thing that we had in the static representation. So let's put the velocity in green vector, the initial position of the vector and its components. Let's divide it by 2 and let's see what changes here. So now we have the circular motion with the vector representation. So we see that unfortunately the vector head disappears in some points. What we need to do to solve this is to increase the value of x max here. So let's put 1.2 And let's generate the animation again, and let's update here. And now our animation looks like this. Before generating the animation with the acceleration vector, I'm going to insert here the trajectory. So I'm going to put this in black, and I'm going to set the line type to dots, and I'm going to use parametric to generate this trajectory. So here we have the x component of the position, the vertical component, and sorry, here we have to use a different variable than the one that is used in make list. So let's put TL, for example. Usually we have set this variable to TP, but TP we have used here. So let's use it TL, and let's put its interval from 0 until t there, and let's see how our animation looks. Let's update here, and now the trajectory is drawn as the particle moves. So the idea behind defining Tmax here is that we can generate simulations of motions with more than one revolution. So for example, let's change Tmax here to 2 times the motion period, and let's update here, and now our animation gets like this. And this is interesting to show to the students that the particle passes by the same points in motions with more than one revolution. We can see that now the animation is faster, and if you want the animation to be in the same speed that it was before, we need to change the number of frames proportionally to the time. So let's set the number of frames here to 400, and let's update here. And now we have the animation with the same speed, but now with 2 revolutions. Let's insert the acceleration vector. Let's put it in red. As the velocity vector is going to start where the particle is, and its components are given by these. And I am not dividing it by 2 yet. So as I did in the static representation. So let me update here. And if we don't divide the components of the acceleration vector by 2, the point of the vector seems not to move at all. So let's fix that, making the vector shorter. And now I think its representation is better. We can add other things there. For example, I could insert the position vector, or I could show motion only with the acceleration. So the interesting thing about knowing how to code this is that you can make the simulations you think are best for your students. So this is how I would like to show you today. If you think creating animations like this could make your classes more dynamic, please subscribe to the channel, activate the bell to receive the notifications of our next videos, and thank you for watching.